Example 8 shows us the change of base formula. Um, with the calculator, if you want to try to type this in, you would have to type it in as either log base 10 of 5 over log base 10 of 2, or it might be a little bit easier to type in log ln of 5 over ln of 2. Okay, you can change it to any base that you want, but you would type that in to evaluate that, and I believe you get about 2.322. Alright, so now we're finally on to derivatives of this. Alright, so first, let's see, earlier in the year I showed you that the derivative of ln of x is 1 over x. So let's evaluate y. Okay, I'm going to rewrite this in exponential form here. E to the y equals x. This way I don't have any ln's. I know how to take the derivative of this. Alright, so we're going to take the derivative of both sides of this. Alright, so the derivative of e to the y is e to the y times dy dx. And the derivative of x is simply 1. Alright, so if I solved for dy dx, I would get 1 over e to the y, which doesn't look any better yet. But earlier I said e to the y equals x. So then I can determine that dy dx, instead of writing e to the y, I could simply write 1 over x. Alright, so there is our derivative of our ln function. Now it's worth noting that if we were going to sketch a graph of ln of x, we know it looks something like this. Alright, so if we look at the slope of this, alright, it's all positive here. It starts out very high, and it's getting lower and lower and lower. So our domain of our ln function is just from 0 to infinity, not including 0. And if we look at evaluating the slope, it does sort of match the graph of 1 over x, just from 0 to infinity. Right? This is 1 over x. It's really high as you get close to 0, but it kind of levels out. So that's why the derivative of ln of x is 1 over x. So we have three different things here. So our basic function, ln of x, the derivative of that is 1 over x. It's also the absolute value of x. If you remember from our transformations, the absolute value of x, it kind of just reflects the graph. Right? If you graph that, I believe it would look like that. So then 1 over x, that whole graph looks something like this. And so this kind of matches that slope. It's just now we can put any number into this, okay, except for 0. When we have ln of some other function other than u, it's just going to be 1 over that function times the derivative of the inside, and if you want, you can place that on top. Alright, so let's find the derivative of each of these. So f prime of x, the derivative of cosine is negative sine. So we're going to have negative sine of ln of x times the derivative of the inside, which would be 1 over x. And you can write that as one fraction if you want, so we'd have negative sine of ln of x. Oh, thanks. Nope, that's okay. Alright. There we go, over x. For part B, the derivative of ln of x, so y prime equals 1 over the inside, which would be 1 plus ln of x, times the derivative of that function, which the derivative of 1 is 0, derivative of ln of x is 1 over x. And then I could rewrite that as one fraction, and I could say it's 1 over x times 1 plus ln of x. Alright, and then we have our last one here. Now, with logs, if you know your properties, we can rewrite this, and it might make our derivative easier. Alright, so I'm going to start off, instead of writing square root, I'm going to write this as to the 1/2 power. And we know, because of our properties of ln's, I can move that to the front. So now it's 1/2 times ln of 3u plus 2 over 3u minus 2. Alright, and then I can even rewrite it a little bit more. I'll put my 1/2 here in the front. And because I'm dividing two terms, I could do this and break it up into two logs being subtracted. Alright, come on. Alright, so now I can take the derivative from this point. So now I'll take the derivative of this. So I'll get f prime of u equals, and the 1/2 stays there. The derivative of ln of 3u plus 2 is just going to be 1 over 3u plus 2 times the derivative of the inside, which would be 3. But I'm going to write that right at the top there. Alright, then we have minus 1 over 3u minus 2, and the derivative of that is also 3. So I'll put that up there. We should probably combine these fractions. Instead of writing the 3 on top of both of those, I'm going to write the 3 out in the front. I'm just going to pull that out. So we're trying to find a common denominator here. Alright, so 3u minus 2. Our common denominator, so now I have a 1 up here because I factored out the 3. But I'm going to have to multiply the numerator and the denominator by 3u minus 2. So I'm going to just combine this. Alright, we're just combining our fractions. So on the left, I'm going to have 3u minus 2. That's what I would have to multiply this first function by. Minus 3u plus 2 over here. Okay, don't forget to distribute that negative. So then I'm going to have 3/2 times, that's half, okay, 3/2 times 3u minus 2 minus 3u minus 2 all over 3u plus 2 and 3u minus 2. Now, if you have recognized that those are conjugates, we can combine those. 3u minus 3u. Alright, so I have now 3 over 2 times negative 4 over, and multiplying conjugates, I'm going to get 9u squared minus 4. Alright, and then we could just simplify a little bit more because 2 and negative 4, I can reduce that. So I'm going to end up with f prime of u equal to negative 6 over 9u squared minus 4. So that's our final derivative. So we could have started way back in the beginning. We could have done ln of 1 over this times the derivative of that. And there we'd have to use the chain rule, the quotient rule. Alright, or we could simplify early and often, and then it's a little bit easier to take this derivative. Okay, use the change of base formula to find dy dx. So we can turn this into ln here. So I'm just rewriting the y function now. So I can write this as the ln of x over the ln of b. Alright, so ln of b, that's just a constant. So I'm going to rewrite that in the front, just so we can see that this is separate here. So it's a constant number times ln of x. If I was going to now take the derivative, okay, dy dx equals it's going to be that constant value times the derivative of ln of x, which is 1 over x. Alright, so the derivative then is just 1 over x times the log of the base, or it doesn't matter what order you write it in. So there we go. So we're just doing 1 over the log of the base, or the ln of the base, times 1 over x, when we are taking the derivative of the common log. Alright, so here's an example of that. We're going to find the derivative, so we're going to do f prime of x equals 1 over the ln of the base times 1 over the inside function. And using the chain rule here, we have to take the derivative of the inside, which in this case is going to be negative 4x cubed. Okay, we can rewrite that as one fraction, and we could rewrite it as negative 4x cubed over ln of 3 times 5 minus x to the 4th. Alright, and that should be fine. This next part, log differentiation. Alright, this is a different kind of technique. If we are differentiating an ugly expression with lots of factors and a product and or quotient, we can make it, this is an easier way to take the derivative. It's part of that simplifying early. Alright, if we have some kind of function, so this, I told you you weren't ready for it yet, but now you are. If we have a function to the power of another function, we want to use this log differentiation. In the third case, when you'd probably want to use it, is if the directions say use logarithmic differentiation. Alright, so let's take a look at this. What a beautiful function there. It looks like if we were going to do this, we would have product rule on the numerator and denominator, we'd have chain rule, we'd have a quotient rule, so we can guarantee that this looks like an ugly function. Alright, so what we can do is start off, before we take a derivative, take the ln of both sides. Alright, so when I take the ln of this, remember when you're multiplying functions, the ln of two functions being multiplied, we can break this apart as adding. So we're going to have ln of e to the x plus ln of x squared plus 2 to the 4th power. And when we're dividing, we can subtract the logs. ln of, and I'm going to rewrite this to a different power here. So instead of writing cubed and square root, I'm going to write it to the power of 3/2. And then we'll have minus ln of x squared plus 3 quantity squared. Okay, so before I take the derivative, I still want to simplify this a little bit. So I have ln of y. I can bring this exponent to the front, and ln of e is just 1. So we have x. I can bring this power to the front. Alright, so 4 ln of x squared plus 2. I can bring this power to the front, alright, minus 3/2 ln of x plus 1. Okay, and then minus 2 times ln of x squared plus 3. So now we can take the derivative. The derivative of ln of y is 1 over y dy dx. Derivative of x is just 1 plus 4 times, and the derivative of this would be 1 over this times the derivative of the inside, which will be 2x here. minus 3 halves times the derivative of ln of x plus 1, which would be 1 over x plus 1. Okay, times the derivative of the inside, which is just 1. And then we have minus 2 times 1 over x squared plus 3. Okay, times the derivative of the inside, which is 2x. Okay, and the only thing, we still have to solve for dy dx. So let's rewrite some of this. Dy dx equals 1 plus, and I'm going to combine this here, so I'll get 8x over x squared plus 2 minus 3 over 2 times x plus 1. Okay, minus 2 times 2 is 4x over x squared plus 3. And then to solve for dy dx, what I had to do was multiply both sides by y. Instead of multiplying by y, though, I'm going to write this part. Alright, so e to the x squared plus 2 to the 4th, all over square root of x plus 1 cubed times x squared plus 3 squared. There we go. So even though it's a really ugly function, we were able to do this without a lot of stress or the quotient rule and multiple applications of the product and chain rule. It was easier to just break it down into usable pieces and take the derivative. Alright, so we can still do that with this problem here. Alright, so take the ln of both sides, or we don't have both sides, so we're going to set it equal to y. Okay, so you have to have two sides. Ln of y equals ln of sine of x to the cosine of x. Using our properties of logs, should be next there, we can move that exponent to the front. So we have ln of y equals cosine of ln of, or cosine x times ln of sine of x. And now we can move on to take the derivative here. So 1 over y equals, 1 over y dy dx, don't want to forget that, equals the first function times the derivative of the second function, which would be 1 over sine of x, 1 over sine of x, times the derivative of sine of x, which is cosine of x. So I'm going to write that right up here, cosine x, plus the second times the derivative of the first. So we get ln sine of x, and I'm going to run out of space here, sine of x times negative sine of x. It's not divided, I just can't fit it, times negative sine of x. Alright, and then don't forget we have to multiply both sides by y. So dy dx equals, this is cotangent here, so to save a little space, I'm going to write cosine x times cotangent x. Plus, or I could say minus, so I don't forget that negative, minus sine of x times ln of sine of x. Ln sine of x. And this all has to be multiplied by that original function, which I can't fit. Alright, so pretend I could write that right there. Sine of x to the cosine of x. So you know, for part C, you know what the derivative should be. It should be 2x. I want you to try to use this log differentiation to find the derivative. And then one more, and this one won't be too many steps here. So I'd like you to do these two problems. Alright, and then maybe a problem or two, but I bet you probably won't because this is about a 20-minute video. Alright, so We'll talk about the rest of this in class. Have a good day.